Hi there. In this video, we're going to be talking about Lagrange multipliers. Lagrange multipliers is a technique that's used in optimization problems. What happens is that there is a function z of x and y, and we want to find the stationary values of z. Remember that the stationary values correspond to maximum and minimum values of the function. And in real life, we want to find these values because they represent some kind of optimization case. We want to optimize cost, we want to maximize profits, and that sort of thing. So in Lagrange multipliers, we're finding some kind of optimal solution or some kind of point, stationary point of z, but subject to a constraint. And that constraint is also a function of x and y. It's an implicit function specifically. To give a practical example, we could say, for instance, that we want to design and build a tank. Maybe this tank could hold water or whatever it is the case. So it's going to cost money to fabricate this tank. And this tank should also hold a specific volume of water. It should hold a certain amount of water. So what we want to do is minimize the cost of the tank. So how do we minimize cost? Well, we minimize cost by minimizing the surface area. Remember that the surface area represents the amount of material that's required to fabricate this tank. And therefore, by minimizing the surface area, we're minimizing the amount of material that we need. So minimizing cost can materially manifest by minimizing the surface area. So we could think of z as being the surface area, and this is a function that we want to minimize. So z, we could think of this as being the surface area. It's a function. And the variables, instead of x and y, we would have r and h. So r would be the radius of this tank, and h would be the height of the tank. So z is a function of r and h. We want to minimize the surface area. So one could argue that the minimum surface area is just 0. It doesn't make a lot of sense, right? I mean, if the surface area is 0, we wouldn't literally have a tank. So there must be some constraint that we need to minimize the surface area. There must be some limiting factor. And that limiting factor is the volume of the tank. We want the tank to hold a certain amount of water. So we could think of this constraint as being the volume. So in Lagrange multipliers, in these types of optimization problems, we have a function that we're minimizing and some kind of constraint that we have, which we need to consider. So we'll begin the analysis by looking at the curves of multivariable functions and then putting on top of that this constraint, and then looking at the technique thereafter. So in the previous example, we just considered a function x squared plus y squared. That is the previous videos, that is. This curve or this surface was drawn in the first video in this series. So just to quickly draw it again, we have z as a function of x and y. And what this looked like was a champagne glass. Okay, it's a very poor looking champagne glass, but you get the idea. So if we take different values of z, in other words, we cut it at different values of z, and then draw that projection on the xy plane, what we would get is a series of circles. You can imagine if you're looking at this from the top, you can see a sequence of circles. I'll just redraw the graph because it just looked too bad. z, y, and x. Okay, I think that looked a bit better. So we can imagine that for different values of z, we would see different circles on the x-axis. So when z is equal to 0, it's just a point at the origin. Then we can have our different values of z. And this is the xy plane. So each of these circles correspond to different values of z. They are the level curves. So this could be perhaps z is 1, we could call it z1, z2, z3, z4, etc. So this is the projection of that surface. So how now do we relate this to our constraint? Our constraint comes about as an implicit function. So we could think about some implicit function that's acting on this level curves, and it could be something like this, for instance. Maybe it's acting like that. We see that there's an intersection with one of the level curves with our constraint. We could see that if we go up, we see that if we go up, we have our surface, the function z that we're trying to minimize, and we have the constraint phi that is actually being applied to it. So just to summarize, these level curves represent the function that we're minimizing, and the red curve represents our constraint. So the intersection of one of our level curves and the constraint is our solution. And at this point, we see that they have the same gradient. So that logic is what informs our analysis thereafter. So the first step is to write our trusty differential for the function z. And we saw in the previous videos that this was dz dx times delta x plus dz dy delta y. So the first point that I think needs to be made is that this level curve corresponds to a constant value of z. So if, for example, we said z is equal to 4, perhaps z is equal to 4 there. So this function becomes x squared plus y squared is equal to 4. So this is a constant, z is a constant. And of course, the derivative of a constant is 0. There's no change because it's constant. So this delta z is 0. And then we divide this function differential by delta x. When we do that, and then of course taking delta x to approach 0, as we've done in the previous video, please look at the video on function differentials if you're feeling a bit lost. Once we do that, we find that we get something like 0 is equal to dz dx, and of course delta x divided by delta x is 1. So we have plus dz dx, sorry, dy, dy dx. So the next step is to make dy dx the subject of the formula. When that happens, what we're left with is dz dx divided by dz dy. So you might be wondering at this stage, what is the point of this? Where is this heading towards? Well, you'll see it in just a minute. The technique, how this manifests in a certain technique that will enable us to solve this optimization problem. We now repeat this function differential for the constraint. Remember that the constraint in our example with the tank, which is the volume, this is also some function of x and y, and it's an implicit function. So we could write delta phi is equal to, same thing, day phi day x times delta x plus day phi day y delta y. The key thing here to note is that I said phi is an implicit function. So it's what would happen is that we would have something like y cubed or y squared plus 7xy plus something 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 equal to 0. So please look at the video on implicit functions if you're not sure what I'm talking about. But since it's equal to 0, phi is equal to 0, it means that, again, just like as z was a constant value and it was 0, the differential is 0, it's the same with phi as well. So the same equation repeats itself with respect to phi as well. So we would get dy dx is equal to minus day phi dx divided by day phi dy. Earlier I mentioned that at the intersection of the constraint and the level curve, the gradient at that point is the same for both. So the gradient associated with this level curve and the gradient associated with this constraint, the red curve, are equal. So what we need to do is set this result to be the same equation, set both of them to be the same. So when we do that, we get dy dx is equal to minus day z dx divided by day z dy, and this is equal to minus day phi dx day phi dy. So looking at this equation, well, we can see that the numerator has to be the same as the denominator, and the numerator of the one side has to equal to the numerator of the other side, and the denominator of the one side also has to equal to the denominator of the other side. But not only just equal, they can be multiples of each other. So if I multiply either side by any number, for example 5 over 5, I'm multiplying it by 1, right? But there will be a 5 in the numerator and a 5 in the denominator, and I could do this for any number. So I could multiply it by, for example, k over k, and this equation will still hold true because I'm multiplying it by 1. What I'm saying here is that day z dx can equal to some kind of multiple of the numerator of the other side. Or the numerator of the one side, day z dx, is equal to a factor of the numerator of the other side. And the same is true of the denominator. So we could have day z dy equal to the same factor times day phi dy. So what I'm going to do next is just send this k times day phi dx to the other side. When I do that, I get day z dx minus k day phi dx equal to 0, and I get day z dy minus k day phi dy equal to 0. I can now just call k some other value, just to change it to a positive. I can call it lambda. That lambda is equal to minus k, and I can just substitute it in there. So it becomes day z dx plus lambda day phi dx is equal to 0, and day z dy plus lambda day phi dy is equal to 0. So this lambda is actually what's called the Lagrange multiplier. So what does this mean? This means that we have some equations that we can solve. We know that the constraint must be applied. So we could have the function phi x, which is a function of x and y, equal to 0. We could have three different equations. We need to solve for x, y, and lambda. So we have three equations and three unknowns. So we solve these three equations to find x, y, and lambda. I think this entire procedure is very much illustrated through an example. So we'll just look at that tank example that I was referring to earlier. So we have our tank to hold water. It has a certain radius and a certain height. We want this tank to contain 400 cubic meters of water. And we want to minimize the surface area. So there's a function that we want to minimize, and we have a constraint that we need to apply. So the question is, what is the optimum radius and height? What dimensions should this tank have such that we minimize the surface area and are able to contain 400 cubic meters of water? The first step is to set up our function, the function that we want to minimize, and that's the surface area. We have the top of the tank, the bottom of the tank, and the body of the tank. So the top and bottom of the tank are two circles, and the area of a circle is just pi r squared. So it's the area of the top plus the area of the bottom. And the surface area of the cylinder, or we use the formula for a cylinder, and that's given by 2 pi RH. And if we just simplify this, we get 2 pi r squared plus 2 pi RH. Now the volume of the tank. What is the equation for volume? So we'll call it, we know that we want it to equal to 400 meter cubed, but we need to represent it in terms of the radius and height. So we know that for a cylinder, it's equal to pi r squared times height. So remember that this must be an implicit function, and it should equal to 0, and needs to equal to 0. So that's important to notice. So how we would do it is we would represent it, for example, phi, and then we would say it's equal to pi r squared times height minus 400. So essentially 400 is equal to pi r squared times height. We just take the 400 to the other side, set it equal to 0, and call it a symbol, for example, phi. So our next step is to set up our equations. So what do we need? We need our first derivative with respect to z and with phi. So we need to find day z, day r. If we look at it, differentiate with respect to r, we have 4 pi r plus 2 pi h. Then we find the derivative with respect to h, and that's going to equal to, well, the first term, there's no h there, so it's just going to be 0 since it's treated as a constant. Then we're left with 2 pi r. So we can also find the derivatives of phi. We find day phi, day r. So looking at this, we see that it's 2 pi rh, and the derivative of phi with respect to h is equal to pi r squared. So now that we have set up our derivatives, we can find our equations. So this is equation 1. So remember what our 3 equations are. We can just go back up and refer to them. So there's our equation 1 here. This is equation 1. You can think of equation 2 and equation 3. So we need to set up these 2 other equations. So the first equation, so the second equation, sorry, is day z, day r plus lambda, the Lagrange multiplier, times day phi, day r, which is equal to 0. So day z, day r is given by 4 pi r plus 2 pi h. 4 pi r plus 2 pi h plus lambda times day phi, day r. Day phi, day r is 2 pi rh. We have 2 pi rh equal to 0. Okay, so this is equation 2. Then for the third equation, we have day z, day h plus lambda day phi, day h equal to 0. Day z, day h, that's 2 pi r plus lambda times day phi, day h. Day phi, day h is pi r squared. And this is equal to 0. So from equation 3, we can simplify that a bit. So we can say that lambda times pi r squared is equal to minus 2 pi r. Then we can cancel some of the variables. We see that lambda is equal to minus 2 over r. So we now substitute, we will substitute lambda equals minus 2 over r in equation 2. So we have 4 pi r plus 2 pi h plus minus 2 over r, that's lambda, into 2 pi RH, and this is equal to 0. We're left with 4 pi r plus 2 pi h minus 4 pi h. R will cancel with r. The 2 pi h minus 4 pi h is just minus 2 pi h. So we have 4 pi r minus 2 pi h. This is equal to 0. We send it to the other side. We're left with 2 pi h is equal to 4 pi r. The pi's will cancel. Divide both sides by 2, and we see that h is equal to 2r. So this is kind of an interesting result. What we're saying is that if we have a tank and we're designing this tank with the top on, and we consider it, then we should make the height to be double the radius. That will give us the optimum surface area and therefore the optimum cost to make this tank. So the last thing to do is to substitute h equals 2r into equation 1, and that will give us the actual dimensions. Sorry, that should be 2r. Substitute h equal to 2r into equation 1. Let's just remind ourselves what equation 1 is. It is just the constraint. The constraint that we said, pi r squared h is equal to 400. And remember that this is equal to 0. So we have pi r squared h minus 400 equal to 0. We substitute this 2r in. So we have pi r squared times 2r minus 400 equals to 0. And we just solve for r. We're left with 2 pi r cubed minus 400 equals to 0. So if we solve for r, we see that r is something like 4 meters. And remember that the height is equal to 2 times the radius, so this is approximately 8 meters. So this is an illustration of how we can find the dimensions of the tank that will give us the lowest costs, that is the lowest surface area to hold a certain amount of water, that's 400 cubic meters of water. So this is the method of Lagrange multipliers. To put it in a nutshell once again, the derivation of the method uses our function differentials, which we have covered in earlier videos. The principle just requires us to recognize that the function that we're minimizing has different level curves, and we look at the projection of the level curves that is on the xy plane, and then we look at our implicit function, which is the red curve, that corresponds to our constraint, and we look at the intersection of our constraint with our level curves. We see that they have the same gradient. Therefore, we write the gradient in terms of our variables, that is z and phi, and we use it in terms of our function differentials. And once we do that, and we set dy dx for both variables, that is for z and phi, then we end up with dz dx divided by dz dy equal to d phi dx divided by d phi dy. And we see that the numerators and the denominators can be factors of each other. And this factor is what is called a Lagrange multiplier. And then we create these two other equations, which is what I put an asterisk next to now. And this together with our constraint equation gives us three equations which we can solve for x, y, and lambda. Remember that our problem is we need to find the point, the stationary point of our function subject to this constraint. So we are solving for x and y. This is the point that is the objective of everything we're doing. And we use the example of the cylinder. We see that we want to minimize the surface area, that's our function, z. And our constraint is that it must hold a certain volume. So we create the implicit function in terms of volume. And we then create our three equations. Remember, the two equations are dependent on the derivatives. So we find the derivatives, we set up our three equations. We then solve for our three variables, that's r, h, and lambda, and then we come across our optimal solution. And our optimal solution says that when the radius is 4 meters and the height is 8 meters, then we have minimized the surface area and subject to the constraint that it can hold a certain volume. So interesting in this result was the fact that the height needed to be double the radius.